Oop. All right, so how you guys doing today? Doing okay. Well, at least we're about to have a spring break, right? So, okay. So next Monday, but that's true. Okay. So the last time, as you can see, we talked about this one because we wanted to explain or consider the substituent group effects on the reactions, aromatic reactions over here. So when you do the substitutions, the substituent groups on the aromatic compounds will have some effects on your aromatic substitution. So I mentioned here, this is a matter directing deactivator. And these two are also para directing. But based on your benzene, this is slightly off in the reactivity wise. So this is the ortho para directing deactivator. Okay. This is the ortho para activator. Directing activator. Okay. So we talked about why these different groups will show you the different substitutions based on their substituent groups on the aromatic compounds. This will direct the other substitution on the meta position. These two will do on the ortho or para position. So last time we talked about this one, toluene. Okay, and then we also talked about the ones in the halogen group. So basically, quick review. Okay, I'm gonna do a quick review on this one again. So for toluene over here, if you have a substitution on the meta position over here, okay, and then you're going to have the cation over here. Okay, so but if it moves to here, here, and here, whenever you have a 1 over here. Can I show you in the same picture? It's okay. So you can have a 1 over here, right? But the other one is just move this one over here, right? Then you move the cation position over here, okay? And then later you can also change this one to here by just switching this double bond to this side. So then you just go move to here. Okay. Among the three possible resonance structure, this will give you most stable form because of the 3 R groups on this carbocation. Stability is higher. Okay. It's the same thing goes with the para position. So let's assume there's the here. Okay. So you can either have plus over here, or here, or here. Okay. So you can switch the bond over here. So in this case, you can just change over here. So this para position will make the compound, one of the resonance structure will have a carbocation position here. We can find the methyl group on this aromatic ring. So that also has the one most stable form out of those 3. But in a meta position, so this is a quick review. So you can also watch the video on YouTube, much detail. But yeah, just do a quick review. So in the meta position here, you're either going to have a positive position here, here, and here. Okay. So you're going to have move this one here and here. So those positions where you can find the carbocation on this meta position, this the substituted compound. those points is only the ones that has just two R groups. So there's no specifically high instability among those three. So that is why they prefer to have a substitution group on either ortho or para, which will have a slightly more stable form on this resonance form. Okay? So this is why this group on your benzene ring toluene will have a ortho para directing activator. Okay? So the one that is why we talked before this one. Okay. The answer should be this one. They don't want it. Okay. It's ortho and para direct. So this methyl group will direct there's additional substitution on the compounds on ortho and para position, but not on the matter, because of the in the way they can have those groups on their compounds. These two will be more stable in the resonance form, resonance effects on in the middle of the reactions. Okay. Makes sense, right? So this is a quick review. Okay. So let's talk. So that kind of makes sense that this one is the ortho para directing. So we also wanted to know the Y halogen. So this is a quick review again. Okay, maybe it's chlorine over here. So in this case, it's almost the same, but this is also kind of the electron donating groups. As you remember, this is electron donating groups, and this is electron withdrawing groups. Okay, withdrawing groups. Okay. So anyway, so if you have you have addition over here, for example, you have a nitration on this side, okay? And then once again, you're going to have a party charge over here, right? So because this bond was made to bond to the nitronium ion, which is electrophile. So this part, no more double bonds. It's a carbocation. So it's actually the same here. You can go here and here. So that means you're going to have either this point carbocation, but if you move this one, you can switch to here, okay? And then you can move this one to here again, okay? So then you can also have another resonance form that has a particle charge over here as well, okay? But the good thing about this one is this halogen group have 3 lone pair. If you look at the chlorine very closely, it's a group 7 element. So when it single bonded to the agronomic compound, it has 3 lone pairs on it. So it's easily to donate 1 pair of electron to make the double bond down there. And then the positive charge, so lone pair is gone here, but it's double bond now becomes here. So as you can see, there's no the positive charge anymore in this ring structure anymore. Okay, so this makes the high stability on the compounds by just having electron donated to that ring structure. That makes this compound, relatively speaking, a bit more stable than the other. The 2 carbocation position, the resonance form. So this is a better one. Okay, so does it make sense? Okay, so the same thing goes with the para. Okay. So if you put it on the para position too, same thing happened here. Okay. And then you can either put here and here and here. Okay. You see the here switching here or here. So that the para position nitro group here will also make the carbocation position here, 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 which also can have, so once again, if you switch to here again, and also chlorine also can also donate one of the lone pair here again, hydrogen. So either they direct the new substituting group on the compound or through a para, they can have this type of compounds that makes this compounds a bit more stable than the other two resonance form, which you could find the carbocation in these two positions here. So obviously, to make this relatively a bit more stable than the other two, you have to have a positive carbocation should be located right underneath of your halogen groups. But if you do it on the meta position, you're either going to have it here, and then think about it. Just move to here, here, then goes here and here. So those not nearby the halogen groups attached to the carbon, so you cannot have that the stable form among the three possible positions. So that is why they don't want to go through directing the nitration happening on the meta position. If there will be more stable on parent ortho positions because of that halogen that kind of makes the double bond onto their ring structure, which give us very good electron donating groups sort of behavior. Okay, this is what we did last time. Last part of the last lecture was this. Okay, kind of makes sense. Is it? It's just because of the carbocation position where you have the substitution happening in each different ortho, para, and meta position. That is wrong. Okay. All right. So the next one. Okay. Next one is also pretty much the same. Okay. So if I give you this one, which is this one over here, so this also would direct the substitution on the ortho and para position, not meta. Can you guys guess why? It's pretty much the same here. So when you look at the halogen groups over here, if you have the ortho position over here, for example, then you're gonna have a cation position over here, right? Because double bond is gone, that is only bound to this carbon position, which is also position. So this is a positive charge. And then just move and move. That means you can have either here, here, and here. And that makes this one, so whenever you have a resonance form that got your carbocation position right under the carboxyl group here, which will here, then once again, this is also electron donating groups. So as you can see, oxygen is group 6, so it should have a 2 lone pair with the 2 single bonds. So they can have a 6 valence electron. So this one of the lone pair can go down to here, then man makes this one. Okay, so that is kind of a more stable than the other resonance form here. Okay, so that also directs the ortho here, and if you did also para position, it's pretty much the same. It's just because the always double bond move on to one carbon or another, so either ortho or para pretty much do the same job here because of that. Here, this one will go here. So if you just move to this one over here, that goes to also the same position you could have on this position as well. And then one of the lone pair goes down there, that makes So you don't have to have a positive charge included in this the ring structure. So this is why either ortho and para position will be more preferred during the substitution reactions. That is why you have these two substitution position will be a major product. Matter, especially for this the hydrox group, almost 0%. So if you think about the other groups, the ortho para directing, they also have a meta positions product, but very little, like 0.1, 0.5%. But this one is almost 0. So this is very extreme case of the directing only the ortho and para positions. But if you do the meta here, you probably have some idea now. Because meta here. This will have this position here, this one here. Okay. Then you see this one move to here, and move to this one here, and here. So those are the positions you can have, which you cannot have a bit more stable Nernst form. Should be right underneath of your hydrox group, which is you cannot do with the meta position. So this will be not favored by directing meta position. It kind of makes sense, is it? Is it kind of, so only thing you really have to know, these two are directing ortho and para position because it's electron donating groups. So they can make more stable form, which they can carry up to the positive charge into themselves. Then but obviously if it's with electron withdrawing groups, it's kind of working in the other way. Okay, so let me give you one example here. So this is what we didn't do last time. Also this hydroxy group as well. But just remember, so on your exam, only thing you really need to know is if it's ortho para directing or meta directing. That's all you need to know. But and also the reactivity table will be given too. So you will be just it will be quite easier than what we discuss everything here because you don't have to know the mechanism. But they will definitely help you to kind of understand it better anyway. So I'll try to. Okay. Okay. So if you have, for example, benzaldehyde, so you have this one over here, which is also which is actually meta directing now, not ortho para directing. And now you guys want to know why it's now only meta directing, not ortho para, because it's electron withdrawing groups. And also, if you look at this one over here, this one is the electronegativity wise, it actually having slightly negative charge because oxygen is quite electronegative. This carbon right next to the oxygen obviously very pro in electron because these two are very strongly bonded. It's double bond here, right? It's carbonyl groups. It has a very strong, very high electronegative elements bond to that this carbon here. This will be very electron density wise poor. Okay, so it's become slightly positive charge in this carbon position here. So if we try to put the ortho or para position once again, and then let's try to put the positive here, right? So let's move here and here, okay? So let's try to move this double bond here in a row, so it'll be here and here. So if you put the carbocation right underneath of that carbon, which is very electron poor, okay? And then if that is happening, okay, if that is happening, you like before, once we had a hydrox group or chlorine, they do what? They donate the electron to themselves. And also you have the methyl group over here. The two will actually make a more higher stability of the carbocation. But in this case, the problem is this is a electronegative. This is not so much. And you see this, the positive charge. This is only slightly positive, but this is a carbocation. So this will become least stable, not most stable. So when you have those electron donating groups or the methyl groups, that makes higher stability out of this resonance form. But in this particular case of your ortho group directing here, that makes very unstable because of this the carbon is very electron poor, and you position the carbocation right under that carbon, electron poor carbon, that makes what? Very unstable resonance form. So that is why so same thing here. If you put this ortho position here or para position, the carbocation position will always going to be what? Here, here, here. So this is why this would not prefer the para position here, but meta, because in that way they can avoid this least stable form by just putting. So let's do this again. So if you do this way in the meta position, and you're going to have a carbocation here, here, and here, which you will not have this type of discomfort. So this one will have not the least stable form, but just the same unstability on those three, which is better than the other. Ortho and para will have a least stable form, but this one does not have to. So that's why whenever you have electron withdrawing groups, that will actually direct your substitution reactions happen at the meta position to avoid the least stable form. So only difference between these two and this one is the one preferred ortho para, because this is where you can have a higher stability of one of the resonance form, but this is the other way. They actually wants to avoid the least stable form, so they can have a relatively speaking more preferred on the meta position substitution. But on the exam, I'll definitely make it easier. I'll show you let's try to do some practical problems here. So I got one here. Okay, so let's try to do, we're learning these two not only for the ortho para or meta directing for one step, but maybe we can have this one. So you have a di-substitute compound here. So not just one. Let's say we have a two. Okay. So now you have this group here and this group over here. Okay. And then you try to do substitution again. Okay. So what's the case over here? So if you try to substitution over here, the good thing about this one is this is also para-directing activated. So either they want to do the substitution on here or here, right? Because it's also para position from here will be this one and this one. But the problem for the para position, they already have another substitution here already. So they can only do what? These two positions. Makes sense, right? And then this groups will have what? Meta directing. So from here, meta position is here and here. Okay? So the substitution will happen here, these two. Makes sense, right? Because this is ortho para directing is here or here, but they can't do it because it's already some group there. So they can only do ortho directing here. This one is also good, okay, with those two positions because it's a matter position from here. Right? So then your product will be this one. Okay? Makes sense, right? Because it's a meta position from here, which is okay. This is meta directing groups. This is ortho para, but they cannot do para because of this one, but ortho position is overlap on those one. So obviously, okay, that might be the best position they can do substitution. So we'll have this one. So as you can see, either you do this one and this one, they're same thing, right? You can just flip it. So this will be your product. Makes sense, right? So it's much easier that way. If you look at the practical exam problems, you just need to look at the substituting groups and which position they prefer to do the substitution. If that overlaps, that's the best position for them to do the substitution. So this will be the product. Okay. Let's do one more. Okay. So if that is the case, how about we have a contradiction? Okay, so those two both group now have okay with a certain position, so we had no problem making a product. But if we have this one instead, so you have a Helix group over here, and you have a methyl group over here. Okay, so if you have this one, now you have a problem because they both also para-reacting, so they want to do. Let's try to do nitration here. Nitration. Okay, so the problem is they want to do here. They can't all pair to each other, right? So they can only do ortho here. So they do ortho position in here and here. Then you don't know where you need to put it, right? Because you have a lot of position they prefer here. So in this case, you need to have this table. So if you look at the reactivity table, this is more reactive, less reactive over here, right? And from here, which one is stronger? This is stronger, right? It's on the right side. So then they take the stronger power to overrule the other, because this is more reactive. So your product will be this one. Okay. So they couldn't do this position much because this is weaker than this one. So this is the stronger ortho-para-reactor activator than this one. So they're gonna do these two. They're gonna do these two because this is stronger. This is more reactive, okay, on your scale. So in that case, this is the product. Okay, makes sense, right? So if they contradict to each other, they choose the higher reactive one, which will be given on the exam, which is you can just see this is stronger than this one, right? And just put it there. Also, position will be the product. Okay, so let's do one more. Makes sense, right? Okay. So let's do one more. That one was the. Okay, so this is a bit tricky one. That's why but this one here. So let's try to do chlorination here. What's AL? Okay, doesn't matter. Okay. So anyway, so if you do this one here, you can also do the same here. So we also position here. This is also para-reacting, right? So they can do these three. You can also do position here, okay, and also para position over here. Okay, so now you can say, oh, there might be a lot of points actually overlap together. This position is also overlapped. Those positions also prefer the same in here. So you can try to do you can do this one. Okay, this is added here. So the one isocycle is the newly substitute. Okay, so this is previous. This is previous. Okay, and then you have another one, of course. This is this position here, right? So here. This is newly added. So one cycle is newly added. This is already there. This one. Okay, and then you have another one, right? Looks like this. And here you can add this position here is also overlap, right? Here. And then here's the thing. In this case, these two are good. This will not form, even though it's overlap here. Because this is one exception I want you to remember. Even though they overlap on here and here, because of the static hindrance. If you look at those two positions here, relatively speaking, it's more open to the space. So they can easily do those position directing substitution. But here they don't want to do much because they do have a sort of sort of meta position to each other, and in between there's a lot of stress they need to do the substitutions. So this one will not form, okay, not so much. But these two will be more preferred because just the static hinderness wise, it has much less space problem, but this is not so much. So they don't want to do this, but these two is overlap together, right? So this is the two product you'll see on this reaction. Even though it's possible theoretically, because of the another problem, which is a spacing problem, they don't want to do that. So these two, okay. So that's a tricky one, okay. Let's do. Okay, can you guys try this one? Maybe I'll give you one problem. I'll give you about. Okay, this is one. Oh, sorry, that's. And you're gonna do the chlorination. Okay. Maybe you can try this one. About 1 minute, or 1 or 2 minutes. Okay, so you see this is a matter directing, this is also paradirect. This is our only thing you have to do. Okay, so you see then, right? So this one will be meta position here, okay? For this one, also position, but this you can do this side because it's groups already there, but ortho and para. So what's the two position you can do? Either this one, right? So then you can do here. Makes sense, right? Yeah. This is there's ortho, para, meta, meta. So these two positions would be perfect substitution place. So these two. Okay. Okay. So just do one more, and I'll finish it. I promise you. Okay. So let's try to do one more. The other one was this one. You have this one. This one has. What's a carboxyl group? It doesn't matter, but you know this is still electron withdrawing groups, right? And this is and let's try to do formulation for substitution. Okay, let's try to do this. It's pretty easy, right? This one is quite straightforward one. You see. Okay, so you see that, right? Ortho and para position, ortho and para position, but it can't do para because of this group here. So they can only do ortho here, which is okay by this one because this is an actual meta directing. So actually the there and here. So your product will be looks like So you can do either here or here, but they're the same thing. You can just flip it. Okay? So this is the problem. We good, right? I think the exam problem-wise is quite easier and quite straightforward. But only the the tricky one we discussed before. But obviously, you just need to follow the ortho and meta para directing groups and see if there's best position for the substitution. Can I move on? Okay. Oh, good. All right. So let's try to do. So we are almost done with the chapter 16. Okay, we're almost done. I think we can finish it by on Wednesday. But yeah, and then we'll move on to chapter 17. So the other one I want to talk about is the nucleophilic aromatic substitution. Okay. So we talked about the electrophilic aromatic substitution for like a week now, right? This is I'm only going to do this briefly because this is very rare. This is not so common in the aromatic compound reaction substitution, but there was only a very few cases we can try to do. So I'm just going to show you real quick, and I'll just move on. But because this is very, very rare, it's not so common. The most common thing we see is what we discuss over a week. That's what we talk quite a long time together. But anyway, so whenever you have I have this one here because of this is one of the good example. So if you have some type of like a very strong base, like a hydroxide anion, you're strong nucleophile, because this is something negative. You're looking for something that is positive, so it's a nucleophile here, right? So instead of we having electrophile before, in this case we actually use the nucleophile. So that's what we're calling this nucleophilic aromatic substitution here. And I put, do you see this? I put also this nitro group here because for this one, for nucleophilic aromatic substitution, you need to have electron withdrawing groups has to be on is the where the substitution happen on the ortho or para position. I'll explain why maybe today on Wednesday as well. But let's try to look at why is it that way. So if you have this group on the meta position, you cannot do this nucleophilic aromatic substitution. So let's try to look why. So you have this one over here, but if you look at this carbon here, so you have a carbon over here, right? This carbon will be, relatively speaking, very electron poor. Why? Because of this one, right? So this one will take quite a bit of electron density to this halogen group here. So relatively speaking, this carbon is quite easy target for this one, because this is something looking for something positive. But among those carbon, this might be the best one to attack. So what they do is do this one over here. Okay. So when they do this one, what happens to this one is they have so you see the negative charge, so this will become neutral. This becomes neutral, right? And this negative charge move to by switching this double bond here, located in here. So this is kind of a vice versa, as you saw before, because So do you guys remember when we have an electrophilic attached to this one here, you had a what? Carbocation, right? But this is now have a nucleophilic attack. So instead of carbocation, you should have carbanion in this position. Makes sense, right? So if that happens, okay, if that happens, this one ever become, so not carbocation in this case will become an anion because it's the opposite reaction. So this one goes to this one, okay? This one, okay? Then goes to, electron goes to next. This one goes to here. Let me do this again. So you can't not have this one. So this goes to here. So electron goes on the top. Okay. So this is weak gone. And then the funny thing is, they move down to make a double bond here again. So yeah, this is, I know it's kind of confusing. So once they have a carbocation position here, they goes to here and move to here. And then when they have a negative charge, they move down to here to make a double bond and move this on to here. Then they make a double bond here, and this one goes to here. So the chlorine will be substituted by this one. Okay, do you guys see this? So carbanium here, move to here, down, down, and down. So they leave. The chlorine will leave. Okay, so I'll stop here. I'll show you again on Wednesday. But this is just totally opposite what we saw from the electrophilic aromatic substitutions. Yeah, let's do this on Wednesday.